We're going to talk about concavity today. It's really just another tool to do more curve sketching. Curve sketching is all about finding specific details of the graph so we can mark them. They're details where something interesting is happening. For example, let's look at a curve sketch we did yesterday. This was one we didn't actually get to, but now I've done it. If I wanted to know any particular other point on that function, I can always just plug the x value in and find the y, right? Like we can always do that, but you don't want to do that for 1,000 points. That would take forever. I mean, quite frankly, we have graphing software now too, so you wouldn't ever really do that. But if you needed to know one particular point, you always could. So sketching is about finding interesting points, points where something's happening, points where something's going on, right? And so where it's increasing and then it changes to decreasing, or where the derivative is 0, maybe it's increasing, derivative is 0, and then it's increasing again. Like those are places where something interesting is happening. So this is another tool where something we might think is relevant or interesting, or there's something changing in the graph. Okay, it has to do with concavity. And spoiler alert here, it has to do with the second derivative, which we've talked a tiny little bit about, but that's just when you have a function, you take its derivative, and then you take the derivative of the derivative. That's all that is. So let's take a look at what that means. We're going to look at a demo, so you don't have this. You're just going to watch for a minute. Okay, let me explain the curve on our left. The green curve is the original function. That's f. You can see the check mark f. I can change them, right? I can add and subtract. So this is f. And this red curve on the right here is the derivative of f prime. Does everybody get that? And this is something we already know, but it's nice to review. So here's a point, and it has the same x value. And this is what we know that the derivative tells us. At the same x value, it tells us about the slope of the tangent. So what happens when this point is going to get to this turning point here? Well, we know that the derivative will be 0. And this is the whole thing, that first derivatives table that we've been doing. Look at the derivative point now. We're looking over here. It's positive, then it's 0, then it's negative. What does that tell us? It tells us it was a local max because, let's see if I can do this, because it was positive, so positive slope, and then 0 slope, and then negative slope. So it has to be a local max. That's how we were visualizing it on paper, right? Okay, and then here's another one. It is it's negative now, right? Like the point is in the negatives, and the slope is negative, has a negative slope, and then it's 0. That's at when the derivative is 0, and the tangent line is horizontal, and then it's positive. And similarly, that's when we have a negative slope, and then 0, and then positive slope, and that has to be a local minimum, or maybe like a global minimum, but anyway, some kind of minimum value, right? So here's the question. What's the relationship between, there's the second derivative, and we saw the original function was cubic, the derivative was a degree 2 parabola, and the second derivative, or the derivative of the derivative, is linear, right? So the degree is dropping by 1 every time, 3, 2, 1. So same thing, actually. Let's just look at that now. So, and now you can forget about the original function. You can just say, okay, the blue line is the derivative of the red line, okay? And so same thing happens, same relationship between the second derivative and the first derivative is the derivative, the blue line is negative, and then it's 0, and then it's positive. And what happens? You have a turning point in the first derivative. Does that make sense? Because it's the derivative of that function. Everybody okay with that? It's the same idea. It's just as if I introduced this to you and I said that the red line was f. Doesn't matter that it's a derivative. The second derivative is still the derivative. Okay, so here's the question. What's the relationship then between the second derivative and the original function? So we notice that the second derivative is 0, 0, 0, 0, 0, 0. Sorry, negative, 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 negative. Then it's going towards 0. Then it's 0, right around there. It's hard to get exactly on. Then it's positive. What's happening in the original graph? Does anybody see it? It's harder to see. What's happening? What's interesting? Something interesting is happening when the second derivative is 0. Emma, what do you think? Yeah. That's exactly right. If you didn't see the hand signals, she used her hand to say it's switching from being like this to like this. That's exactly what concavity is. If you've talked about concave and convex in science class, it's the same idea. Concavity, concave is the same idea. Okay, we don't talk about convex though, really. And that's exactly what concavity means. Okay, and so the second derivative tells us about the concavity of the original function. So let's go back, very good. So let's go back, and actually I'm going to go to the bottom of this page, and we'll just do a quick little definition here. So when I have a curve like this is concave up. And when I have a curve like this is concave down. And I think of this two ways. The concave down kind of looks like a parabola that's opening downwards. And the concave up kind of looks like a parabola that's pointing upwards. But so that's one way you can kind of think about it. But the way I actually personally just think about it is like, I think about going from x's, increasing x's, which means I start on the left, and as I'm going this way, if I'm concaving up, I'll eventually be going up. You know what I mean? So I'm coming around this way, and as I'm concaving down, it's going to eventually turn down. Like it's not turning down yet, but it's kind of on the way to turning down. Does that make sense? And so if I change from concave down to concave up, it's like I'm going to be turning down, now I'm turning up. Okay, and that's called a point of inflection. When it changes, concavity is a point of inflection. We should probably write that down somewhere. And point of inflection. Thought I turned that off. And the other thing I'll say, which we'll talk about a bit more as we get through this, the trickiest part is concave up. Even though we think of it, and I think of it as eventually it's going to be pointing up, that's not actually exactly true. Because if I have a asymptote, a horizontal asymptote, okay, and I'm coming down towards it, this is obviously concave up because it's curving in such a way that it'll eventually go like that. Except that if it approaches the asymptote, it never actually does go up. But that curve is certainly not concave down, because concave down would be doing that. So which one is it? It's concave up, but it's concave up in this strange way where the amount that it's concaving is constantly decreasing, so it's approaching the asymptote. So it's a special kind in some ways, and it's the hardest one for people to put their finger on. Okay? Okay, so let's take a look. You have this sheet. So we're going to look at the point. Whoops. We're going to look at the concavity. And then we're going to look at the second derivative. We'll just call it f prime. F double prime, I mean. Okay? So we'll call this point A. What's the concavity at A? There's only two choices, concave up or concave down. What do you think? Down. So point A is down, which means the second derivative at that point will be negative. That's the important connection. Just like we know whether the first derivative is positive or negative. That's what's important. Okay, and then B, is it concave down or concave up? Emily? Up. So what do you think? Obviously positive. And so there's been a point of inflection there because it's changed. Where exactly is it? Ooh, that's hard. That's hard to pinpoint it, but I mean, it's somewhere in there, right? It's not necessarily on the x-axis for this graph. I don't know where it might be, but it's not necessarily. Okay, it is hard to pinpoint. Okay, let's do C. Is concave down, I think? Yep. So it's negative. And D, it's still down. So it's still negative, right? Hasn't changed. And that looks like it's going to be asymptotic, so it would always be down. It's not going to change back up. They obviously don't always change. Oh, man, we're so running out of time here. Here, I want to show you one more quick thing. I forgot to talk about that. Back to this. The point of inflection happens in here somewhere. It's hard to see. But we can see that it happens when it's 0, but it's hard to see just by looking at the graph. But if I change this function to be something like this, then it's kind of easier to see, isn't it? Like it's right there. It's at the twist. It's at the cubic twist that it's happening, right? Where it's concave down here and it's concave up there. So sometimes it's easy to see. Sometimes it's not. That first one, you could kind of pinpoint it. We'll do this one again quickly. We've got A, B, C. That's really all we're going to have time for today. The concavity. So at A, what's it doing? Like trace your finger through it. What's happening there? It feels like it's coming around and eventually going to end up pointing down. So it's down. So it's negative. At B, what do you think is happening? Again, it's kind of, I hope, still feels like it's going down. What's happening at C? Up. So it's positive. This is one of those cases where it's got a horizontal asymptote that it's crossed, and then it turns, and then it approaches from above. And so the point of inflection in these can be really hard to pinpoint visually, but it's in there somewhere. And thankfully, we can calculate second derivatives, and we can calculate the point of inflection by finding where the derivative is equal to 0. That's what's coming. Okay, this is your homework for tonight, but you're not going to be able to do most of it because we had like 2 big sketches that we were supposed to get done, so that's okay. You can definitely do question 1B. If you are ambitious and you have lots of time, you can look at question 2 and maybe even question 9, but question 8 I wouldn't recommend. But 2 and 9, you could at least read and take a crack at. But that will probably just be our homework for tomorrow and for the weekend. All right, so we're just going to try to get through 2 sketches, and we're going to sketch. Notice how it says, it doesn't actually say using concavity. It says showing all points of inflection. So that means like we have to find the points of inflection. And if you recall, that is where concavity changes from up to down or down to up. Okay. And everything else, including critical values. So we have to find those, including what else do we always have to show when we're sketching? Intercepts, asymptotes. So we have to find all of that stuff. But because it also says points of inflection, we will use the second derivative table, and that will allow us to do everything in a slightly different way. But that's okay. Again, the order in which you do things is somewhat up to you. There's no formality here. There's not necessarily a best way of doing it. There's kind of a way that we tend to do it. but I bet every teacher and every person is a little bit different. I'm going to do this. I'm going to factor. This is like a difference of squares, but backwards, right? So, 2. Can anybody confirm that the square root of 9 is 2? Is that right? Am I right about that one? 3 plus x, 3 minus x. And the bottom's not factorable. It's already factored. Can't take it any further. And I'm going to do this to let f at x equal y. And you don't have to just copy me. You can beat me to the punch here. We're going to do the intercepts and the asymptotes so you can get started doing that stuff. And this is really nice because even just doing all these little details, you want to decide which form you're looking at to figure out the y-intercepts and the x-intercepts and the asymptotes, like which form do we like it to be in to determine all of those kinds of things. And remember what I said the other day, every question is a little bit different. It just has a bit of a different feel to it, And if you didn't do enough of these, you could get caught on something small. Has anybody figured out the y-intercept? Nobody? Anybody? 9/4. 9/4. How'd you get that? Maybe this is obvious. I don't know. But honestly, I can imagine some people might have had to sort of really think about that. And then you just worked it out? Often, if it's an expanded form, we see the constants when 0 goes in for x and we just pull it out of there. But we don't have an expansion on the bottom. And the top is backwards. So it's just, I don't know, it just looks a little bit different. But 9/4, that looks good to me. And I'm sure the x-intercepts were straightforward. Okay, keep going. Alaf, tell me about what we do for the vertical asymptote. -2, and then what do I do with that? Very nice. And this is the calculus way of presenting it. The limit as x approaches -2 from the left of y, and the limit as x approaches -2 from the right of y. And again, remember we talked about this quite a bit the other day. This can be very different in different kinds of questions. So and I think it's helpful, and maybe you can't help but do this, but when you're doing it, think about, do I want to use the original form that I was given or the factored form, or which form do I like putting the values into just to the left of -2 and just to the right of -2 to figure out what they are. And we talked about this, that you can actually use -2 on top often. You can't use -2 on bottom because that's going to give you 0, and that's the whole reason why there's an asymptote. But on top you can. Does anybody have what it works out to? What do we got? Positive infinity for both? Beautiful. I don't know if I have this. Very nice, very nice. And the horizontal asymptote. Who's got that? Where does the horizontal asymptote come from? Yeah, so we got to look at the degree on top and the degree on bottom. In fact, that's often something you look at in the beginning to see if you have a horizontal asymptote or oblique. So I kind of took it for granted that these are both degree 2, both quadratic, so same degree. So we don't have oblique asymptote. And so because of the same, we're looking at the coefficients. And what's the coefficient, the leading coefficient on top? Again, this is kind of hidden, John? Yeah, well, something about the 1 though. Yeah, very good. -1, right? Because it's minus x squared. And again, something so small like that is enough that you just don't think about it. So -1 on top. And if you expand it or think about expanding it, +1 on the bottom. So that should give us a horizontal asymptote of y equals -1. And we talked about the trick, and you got that handout the other day about the difference between a horizontal, when you have a horizontal asymptote, that's a number, a horizontal asymptote, that's y equals 0, or an oblique asymptote, and the different cases of degree and how you tell which one's which. Elif? Why do you think so? So I like it. You chose a number. You picked -4. Well, hold on. -4 is pretty far away. I think it's too far. Think about what a graph could look like. Let's see if I can come up with something here. So vertical asymptote of x equals -2. I could be at 4. At -4, I could be down here and be going up like that. So I'm in the negatives. You know what I mean? Like it could be way far off. So we want to use something really close, like -2.1 is close enough, something like that. And then again, you only have to think about the signs. What's the sign on top? What's the sign on bottom? And I would look at this. We can talk about this. Why not? When I put the bottom, I'm going to put -2.1, and I'm going to put -1.9 in there. No matter what I get, it's in brackets, and I'm squaring it, so it's positive. So the bottom is always going to be positive, right? No matter what. Like I can do the limits one at a time, but when you do a bunch of these, you start to realize that when you have something like this on the bottom, something's going to happen. Now I don't have to think about it again. And when I put -2.1 on top, I'm going to square it and get something around 4. And when I put negative, and it's going to be positive. And when I put -1.9 on top and square it, I'm going to get something around 4, because those are both close to 2. 2 squared is 4, right? And 9 minus something around 4 is also always going to be positive. So the top's going to be positive in all those cases. So positive over positive, both of them are going to be positive. But but you don't do it just the way that I do it. Like we all see these things differently. That's why I'm saying that part of the experience is going through that messy mental math of, okay, what am I going to plug in this time, and really coming to terms with that, okay? And then the horizontal asymptote is a very different kind of test. What do we do for this? Oh, this is something, I forgot to do this. I wanted to make the mistake that it was y equals 1. So let's pretend we don't know what the right horizontal asymptote is, and it's And we thought it was 1 because we missed that negative, right? We missed the minus x squared. So we got y equals 1. So what's my test for horizontal asymptotes? Yeah, we test the extremes of the graph. And I can only do this because I said let f at x equal y, right? Otherwise, using function notation here would make no sense. And you'd have to, and sometimes we just write ordered pairs. We just write bracket, -100, comma, and then whatever value we get when we plug in there. You can do that too. Some people like that. So when I plug in here, I get approximately -1.04, and you should do this yourself because, again, plugging into a calculator is a skill and it's something that we should practice. And in here I get -0.96. And now I have to interpret these. And what do I do? What do I notice here? What's going on? And they don't match my asymptote. I said my horizontal asymptote was y equals 1, and I've got two values that are in the negatives. So either we haven't picked values that are out at the extreme enough, and absolutely there are graphs that don't tend to the asymptote until beyond 100. We just don't graph them in class because, you know, we need them to fit around the origin, right? So for us, that's always going to work. But like, I would look at this and I would go, are those above or below 1? I'm like, they're nowhere near 1. My asymptote is wrong. So there's an awesome check for horizontal asymptotes that when you plug in, it'll show you what value it's around. So you could actually do this out of order. You could plug in -100 and 100 and see what value they're around. And they may not shadow because they could both be above. It's not always above and below. And now I got to decide, is this first one directly above or directly below negative? So this one's below and this one's above. Okay. Now we're going to do critical values, and this certainly makes sense to do next. How do we find the critical values? It's the same as we were doing before. Yeah, we take the first derivative. Whoops, so y prime. Oh, and I'm going to rewrite y equals 9 minus x squared over x plus 2 all squared. Okay, and I'm going to y prime. So the derivative of the top, which is -2x times the bottom, minus the derivative of the bottom times the top. Over the bottom squared. Now here's where we've talked about this, and you have to kind of remind yourself to do it this way. I would encourage you to factor here, look for common factors. Remember, that's how we did it in Unit 2, and that's how we've been doing it so far. It's better than expanding and simplifying. Well, I think it's better. You can expand and simplify, but it's more complicated, and I think it's good to try the factoring. But if you decide to do the factoring, you really don't like it, as long as you're doing it right, I guess it's fine. So I can factor out a -2, and I can factor out an x plus 2, which you will basically always factor out the x plus 2. You can kind of expect that, okay? And then what are we left with? We're left with x times x plus 2 plus, careful of that negative if you factor out a negative. The 2's gone, the x plus 2's gone, so plus 9 minus x squared. And this is one of the reasons why I like factoring, because this always works out, and these guys are gone. Remember, we talked about this. When you take the derivative, the exponent in the bottom always increases by 1. And we want to get it to that simplified form. So we want to factor that out. If you do it the other way, you're just going to have a little bit more factoring at the end. You got to make sure you factor that out and get rid of it. Because when you take the second derivative, it's going to be a disaster if you don't have it fully simplified. So on top, I've got negative 2 x squared. We'll just do this in 2 steps. X squared plus 2x plus 9 minus x squared. So the x squareds are going to be gone. And I get 2x plus 9. And what do I do? What do I do with this? What was the point of this whole process? Critical values. Where do the critical values occur? Sometimes we get in the habit of doing things and forget why we do them or what we do them or what the original kind of definition was. What is a critical value? It's where a max or a min may occur. Very nice. How do we find critical values? Or doesn't exist. So every single time, consider both those options. And some people are forgetting that. So get in the habit of doing it every single time. Y prime equals 0 at x equal to something, maybe multiple somethings. Y prime does not exist at x equals something. Why do you think in Unit 2 we did a whole day on this and kind of tried to drill it in, and then it came up over and over and over again pretty much every day since then? So where does y prime equal 0? When the top is 0, where does y prime not exist? When the bottom is 0. So we're just looking for where things are 0. We're good at that because we've been doing that for a long time. So for this one, it is negative 9 over 2. And for this one, it's at negative 2. But that's a vertical asymptote, so I'm done with that one. But it might not be. There are certainly cases where that doesn't happen. And then for this other one, I want to find what that critical value is. And it works out to about negative 1.8. So we have a point at negative 9 over 2 comma negative 1.8. Try to keep your solutions organized because we're doing all this work. And remember, it takes a long time to do all of this. And then, like, we've already been working for like 20 minutes, although we did some stuff slowly. We've talked about stuff, so you can certainly do it faster than that. But we've been working for 20 minutes, and we're not done yet. We're going to do another 5 minutes or so of stuff, and then we have to go back and put it all together to come up with a sketch. So you want to have all the information you need easily accessible, where you can find it somewhere. Okay, and I think I'm going to run out of space, so I'm actually going to move to a second page. And on my second page, I'm going to be able to fit everything else in, including the sketch. Should be able to. Often these guys take 2 pages at this point. Okay. Everybody good? Any questions? Next is points of inflection. We shorten that to POIs, which drives me nuts because that's point of intersection in other classes, and I hate having the same acronym for different things, but anyway. So y prime, I'm actually going to expand it because if it's easy to expand, like if you're multiplying a constant through makes it easier to take the derivative. So it was negative 2 times 2x plus 9. So that's going to be negative 4x minus 18 on top. And the bottom is fine to leave Bottom we want left. And how do we find points of inflection? It's very similar to how we found the critical values, but we use the second derivative, so I have to take the next derivative. So it's the derivative of the top, which is just -4. Why don't you go and give that one a shot? Why would I take that lovely opportunity away from you? There's the first line. And like I said before, now I think we want to factor it. Common factor. Something I was going to say. Okay. Different ways you can do this. I noticed that remember when we multiplied the 2 through to expand the top? Well, now inside that bracket, I've got a common factor of 2. If you notice that, it might be nice to factor it out. Okay? So I can factor out, in fact, I can factor out a -2 from both of those things. But that's not one that will necessarily jump out. And you have to be able to keep track of this stuff and be good at doing this stuff in your head. I think otherwise, you might make a mistake going through here. So hopefully I won't make a mistake. But you could try it. If you see it, it might make your life easier later on. Because I don't think I have any other factors there. So -2, and then, and I have x plus 2 squared. Over x plus 2. And what did I say about the denominator? It's supposed to increase by 1. So I've got 2x plus 2's up here and 6 down here. That simplifies 4, so it increased by 1. So that's exactly what we're looking for. Clean this up a little bit. Oh, something weird happened there. Oh, I'm not done yet. What am I doing? I think it's worth it to rewrite this one more time. What do you think my last step here is going to be? Just to tidy it up. John? Yeah. Multiply the negative from the -2 through, or factor a negative out and multiply by the -2 to make it positive. Either way, It's kind of nice to clean that up, I think, plus 23 for x plus 2 to the fourth. Whew. Now, the problem is, and this is why in the last unit, even though the type of algebra we asked you to do was challenging, and there's all kinds of little details, it's important because if you make one mistake in this process, anywhere along the way, it can drastically change your second derivative, and then you get one little thing out of place, like one negative sign out of place, and your graph won't make any sense. And you won't be able to resolve it, and you might not be able to graph it at all. Like, you're going to get halfway through the graph and be like, oh my gosh, this is just not going to work. It's really, really tricky. Right? Imagine you had the point of inflection, the sign of it wrong. You would be trying to draw a point of inflection in a graph where there isn't one. Really, really tricky. So, that all being said, typically what we do is, so if we do a quiz, you'll have to do the derivatives yourself, but you'll have a little bit more time because it'll just be the one question. But on the test, we'll give you the first and the second derivative. So you don't have to do them, so you don't make a mistake doing them. You just have to know how to apply them. If we end up doing it on the test, we may ask you to do the first and second derivative on your own once, or we may ask you to do that somewhere else on the test, but for the curve sketch, we'll give it to you. Does that kind of make sense? So just a heads up. But you still do need to know how to do this because you will have to do, good morning, a curve sketch from scratch at some point. And, you know, it's a big part of calculus is being able to take derivatives accurately. So now we're going to use this. Oh, wait. So just like I said before, at this step, we want to stop and we want to say, so y double prime equals 0 when, and y double prime does not exist when. I'm going to speed up a little bit here so we can try to get through our second curve sketch as well. I think we have enough time because we won't stop and talk as much about things. So when the top is 0 and when the bottom is 0. But that's a vertical asymptote, as we've already established, so the bottom we're not worried about. But we always have to consider it because it could be a max or a min. And where the top is 0, what is that? A point of inflection. That's a change in concavity. And so we'll see that when we start graphing it, it'll make sense. It'll fit. As if we've done everything correctly, it'll fit and it'll give us new specific information that we can use in our graph that we haven't seen yet. So I'm going to build my second derivative chart here. And we do the intervals the same way, but using the second derivative. So when x is less than negative 23 over 4, at negative 23 over 4, between negative 23 over 4 and x and negative 2, at negative 2 and greater than negative 2. What is negative 23 over 4? Approximately. It's around negative 6. So make sure you keep that in mind. Fractions make it a little bit harder on our mental math. And since we're considering so many other things, even if you're good at fractions, sometimes that's the kicker, right? Because it's not what you're thinking about. You're thinking about all the new stuff, the concavity and everything. But I always like to pick something big, so negative 10. And when I put negative 10 in, again, take a look. The bottom will always be positive. And negative 10 times 4, negative 40 plus 23, that's negative, times 2, that's still negative. So the second derivative is negative there. What does that tell me about the graph? For the first time, Concave down. At negative 23 over 4, it's 0. Between negative 23 over 4 and negative 2, so I got to pick a value somewhere between negative 6 and negative 2. So I don't know, negative 4 is probably good enough. So if I put negative 4, the bottom's always positive. If I put negative 4 in, I get negative 16 plus 23, that's positive. So it looks like this is positive. So now it is concave up. So this is a point of inflection. And we want to know the actual point. So it's negative 23 over 4. And it's approximately negative 1.7 that it works out to. Go away. Okay. At negative 2, it's a vertical asymptote. And concavity could change at a vertical asymptote. That's why we have to put that in as in our table. So then I could pick 0 here. That might be an easy one to use, or some big number like 10. And I think it looks like we get positive over positive. So again, we're concave up. Any questions? Ready to sketch? Yes? No. You do one, or typically we do one or the other. We won't need the other chart. What did we use the other chart for? When it was a maximum or a minimum. So we were testing, is it increasing or decreasing before? And is it increasing or decreasing after? But we have enough information in what we have to figure that out. So, but that's what I'm saying, it's redundant. But we have enough information to figure that out. So let's get started. I'm going to put in my intercepts and my asymptotes first. So scrolling back up, I'm going to look at my page here. Where were our intercepts? We had a Y-intercept at 9 over 4. We have X-intercepts at plus and minus 3. I have an asymptote at y equals negative 2. Sorry, x equals negative 2. My horizontal asymptote is at y equals negative 1. What else? What else? What else? I think that's good. On the vertical asymptote, increasing from the left and from the right, it is going to positives. Horizontal asymptote, the order of this, again, is a bit of an art. It's up to you. When I'm going out to the extreme right of the graph, that was F at 100. It was approaching from above. So all of that information looks to me like it goes like this. And then approaches, ooh, that was a little bit bad at the bottom there, but like that. From above, cuts through those two intercepts. That looks all good to me. The other one, put your pencils down and watch. Approaches from above, cuts through this intercept, approaches the other one from below, and as we just saw, there is a critical value, which means a local max or a local min, right? At negative 9 over 2, so negative 4.5, and negative 1.8. And there's a point of inflection at negative 23 over 4, so that's around negative 6, we said. And we found the value of negative 1.7. So I have and then it approaches from below. So just watch. I have a critical value. It's concave down here in this interval. right? When does it become concave up? At the point of inflection. That happens later on down the graph. This was at around negative 4.5. Exactly, negative 4.5, sorry, negative 9 over 2. I know this is a minimum because of the other details of the graph and because it's concave up at that point, right? And then it hits the point of inflection and then it's concave down. So my point of inflection is somewhere in here, negative 23 over 4 and negative 1.7. And this one is negative 9 halves and negative 1.8. So it's below the other one. Like there's a lot of details to look at here. I'll go over that again. This interval is concave down from our table. That was this one. This interval is concave up, and this interval is concave up. So you have to think about where the point of inflection is relative to the critical value, determine what interval it's in. Is it concave up, concave down? That's how we know if it's a local min or a local max or a max or a min. That one looks like it's a global minimum, not just a local minimum. You got to think through all of that stuff because we didn't do the first derivatives chart. But there's a lot of puzzle pieces that all have to fit together that should. And if they didn't, it probably means you've done something wrong. And like I said before, this is why if I had one of those things out of order, the whole graph would not make sense. Imagine I had that point of inflection, the sign wrong. You couldn't draw the graph at all in any sensible way, right? Holy cow, 12 minutes. We're not going to get a second one done. Any questions? We took our time on that one, I guess. I'll do the other one and post it online and you can take a look at it. Okay? You could try to do it yourself first. That might be great. I'll do a video of it so you can follow along if you need to and put the scanned version up. The whole shebang. But it's this graph looks a little bit different. But it's similar, same kind of idea.